Welcome to the course Advanced Reaction Engineering. So, in this course we were discussing about the catalysis and catalytic reactions or catalytic reactors. So, in that case various type of catalyst we have discussed. Once various type of catalyst we have discussed, after that once a catalyst is put inside of a reactor for a particular reactions. So, the reactant may come in contact with the surface of the catalyst, and there are many or various steps are there. So, that is, let us say, adjacencies of the reactants, surface reactions of the reactants, and then that is converted into the product, and then desorptions of that products from the surface of the catalyst. So, these are the key steps that we are taken, and based on that we will derive some rate law. So, that may be Langmuir-Hinshelwood mechanisms or Eley-Rideal type of mechanisms, Marx von Kraepelin type of mechanisms. So, various type of mechanism possibilities are there. So, how the reactant molecules get adsorbed over the surface of the catalyst. So, that may be molecular adsorptions or maybe dissociative adsorptions, various type of that possibility is there. So, the first we will consider. So, in our case we have said that there is adsorption, surface reactions and desorption. So, first we will discuss about the adsorptions when reactant molecules may come over the surface of the catalyst. So, here's catalyst surface sites, that is we are considering. These are the surface sites, this is the catalyst and these are the surface sites, or you can express in terms of weight. So, where reactants is A and B, that gets adsorbed. So, that may be once A adsorbs over the surface sites A, then it is forms adsorptions of A over the surface sites one single sites, and then B also may be another reactant that also get adsorbs over the surface sites. So, it forms BS. So, you can say like that. So, this is this and this is this. So, this way you can express the reactant, both A and B are reactants that gets adsorbed over the surface of the catalyst. So, in the catalyst surface sites these are the vacant sites. So, where none of the reactant molecule get adsorbed. So, then total surface sites, if we want to consider, CT is the total surface sites, means active sites are present inside of the catalyst. So, the catalyst we have prepared. So, these are the vacant sites and this is the adsorbs the sites occupied by A, the surface sites occupied by the B. So, that is the total surface that is present in the catalyst, that way we can express. So, now if the adsorptions, if we consider this is molecular adsorptions or non-dissociative adsorptions. So, as reactant molecules adsorbs like this way. So, with the surface of the catalyst sites, or maybe different types, means second type, that is the dissociative adsorptions. So, the reactant molecules, let us say two surface sites required. Here one surface sites was required and here two surface sites. This way molecules may get dissociates and get adsorbed over the surface sites. So, now this surface sites rate maybe we can express this way, means molecular adsorptions or non-dissociative adsorptions. Here C molecules get adsorbed and it forms like this type of. So, and here two reactions are there, forward reactions is the adsorptions, backward reaction is the desorptions reaction. This is the forward reaction and this is the backward reaction. So, two reactions simultaneously takes place. So, if it is adsorptions and this is desorptions, means these molecules get dissolved, and means adsorptions and desorptions we are considering as a reversible process or reversibility, then this type of case. So, rate of attachments we can express this way. So, rate of adsorptions equals to rate of attachment minus rate of detachment. So, rate of attachment is this, rate of detachment is this. So, rate of detachment is expressed this way and rate of attachments is expressed this way. So, overall at equilibrium or steady state, that would be the balance. So, that is the rate of adsorptions equals to this subtracted with rate of detachment. So, we can write this. So, rate of attachments, it is expressed in terms of rate constants, forward rate constant, that is capital small k A, partial pressure of CO and active sites, vacant sites present. So, that way we can write. Okay, and desorptions or detachments we can write backward reactions rate constant minus k minus A, and this is k A, forward reactions rate constant k and backward reactions rate constant k minus A. Okay. So, this way you can write. So, that detachment directly proportional to the k minus A into concentration of this, okay, COS. So, now the rate expressions adsorptions we can write this way, we can take k outside of the bracket and then we can write this way, where capital K equals to forward rate constant divided by backward rate constant. So, that way we can write. Okay. So, now at equilibrium the rate of adsorptions equals to 0. Okay. So, the forward and backward both are same. So, then RAD equals to 0. So, then we can write these equations into this way by putting this equals to 0. So, these equations can become this. So, left hand side the concentration of the CO that is get adsorbed over the surface we can write or express this way. So, now the total vacant sites or overall site balance we have said that also you have to consider whenever do such kind of means rate equations derivation. So, total site balance equals to CT equals to vacant sites and means unoccupied sites plus occupied sites, that is the total sites. So, this way CV we can rearrange these equations this way, then we can get CV in the left hand side, right hand side CT minus COOS. So, CV we can substitute here in this equation. So, then we can get this. So, in the left hand side that is the CO that is get adsorbed concentrations of the sites that we can express this way. Okay. So, now this we have received or we have got. So, now we are rearranging these equations. So, after rearranging these equations, after substituting this we can get this, and right hand side also COS is there. So, concentration. So, then left hand side COS equals to in terms of right hand side the terms we can express. So, now these equations we can rearrange this way. Okay. So, these equations we can substitute this way. So, then this and this we can plot, we can do the plots, partial pressure of CO and adsorption concentration of the CO against partial pressure of CO if we do plot. So, the lines will come like this, linear lines will come. So, that equals to, if from these lines if we want to get the slope, slope equals to some value will come. So, that is equivalent to 1 by CT. Okay. 1 by CT equals to slope, and if we extend this line up to this, whatever that gap, that is the intercept. So, intercept equals to 1 by KS CT. So, from intercept and slopes we can find out reactions rate constant and CT value if we do this way. Okay. Similarly, for dissociative adjocencies also, in case of the dissociative adjocencies we said two different sites are required, sites where CO molecules will get attached. So, here this is the sites 1, this is sites 2. So, here dissociatively that CO molecule get adsorbs like this way. Okay. So, C atoms adsorbs here, oxygen atoms adsorbs here. So, two sites are required. So, like this it is forms. Okay. So, rate equation or reversible reactions we can write, adsorption reactions that is the forward, backward reaction is the desorption reactions. So, this way you can, this is forward reactions and this is backward reactions. Okay. So, this is reactions 1 means forward reactions and backward reactions that is we write this way. Okay. So, this way possibility is also that dissociative adsorptions of reactant molecule. So, similarly rate of adsorption by considering dissociative adsorptions we can express this way. So, this also we can write this way. Okay. So, now at equilibrium rate of adsorptions are AD equals to 0. So, if we put then surface concentrations we can get, so that is surface concentrations C or O, C C S or equals to C O S. So, this is the indicate this and this is indicate this, means the oxygen atom that is get adsorbs at the sides and carbon atom that is get adsorbs over the surface side C. So, therefore, we have written this. Okay. So, now if we are getting these equations and total side balance also we can do, and that side balance this way you can write, and there CT equals to CV plus CCS plus COS, CS equals to COS. So, then we can write CV plus 2 CCS, this way you can write. And so, now if we substitute rearranging after substituting this CS value or COS value here, then if we rearrange this, then we can get this. Okay. This CV we can substitute similarly as we did in the last cases. So, then we can get these equations, and these equations we can rearrange and we can express this way. Okay, for dissociative adjocencies, and then if we plot partial pressure of CO to the power half by divided by concentration of oxygen, that is surface oxygen concentrations, this way against partial pressure of CO to the power half. So, then this type of lines will come if we extend that, similarly intercept and slopes will get, and from there the CT and reactions rate constant we can find out. Okay. So, in both we compare, means suppose you have experimental data, and based on that if we see that whether the adjacency is molecular adjacence or non-dissociative adjacent or dissociative adjacent. So, if we plot these C adsorbed CO concentrations against partial pressure of the CO, if the curve is like this, plateau is reached, but here it is linear, and in this case if it is parabolic natures, and then it goes reach plateau. So, if this type of nature is come, so if the adjacent nature is like this, then we can say that the reactant molecules get adsorbed over the surface of the catalyst as dissociative adjacence is there. If it is like this, then we can say it is non-dissociative adjacent. Depending upon that results or plots, we can say the which type of or what type of adjacence is theirs. Okay. And this type of adjacence isotherms usually is called Langmuir type of isotherms. This is means this type of isotherm is called Langmuir isotherms. Okay. So, now surface reactions means adjacence step 1 that we have discussed. Now, step 2, that is the surface reactions. Once it is get adsorbed, then reactions will take place over the surface of the sites. So, then the surface reactions may be different types. So, it may be single sites reactions, means reactant A converted into products, or maybe dual sites, means reactant A, reactant B get adsorbed and occupy two different sites of the catalyst, and then it converted into C and D, and or maybe Eley-Rideal type of mechanism might possibilities there. Reactant A, we have considered that reactions is let us say C plus D here. Reactant A, that is get adsorbed over the surface sites, but B remain in the gas phase. So, here dual side mechanism, both the reactants occupied two surface sites, but in this type of here one reactant molecules might be in the gas phase, and second or other reactant molecules must be occupied some surface sites, and then reactions will take place this way and will give some products. So, this different type of way of surface reactions possibility is there. So, based on this we will develop some rate equations, based on this we will develop some rate equation, this way also we will develop some rate equations. So, based on experimental results, which one will be fitted well. So, then we will consider that the reactions may be single side mechanism, dual side mechanism, or this type of mechanism it is following, means one reactant molecule may be in the gas phase, another one is the means in the over the surface of the catalyst. So, this way you can express. Okay. So, now single site mechanisms. So, here one example is given here. So, here you can see that. So, if the reactions is this type of single sites surface sites, means this way it is happening. So, then rate we can write this way, A dot S, that reversible signs B S. So, A directly giving A interacted with surface sites B A interacted with the surface sites, and it converted into corresponding product B, that is also remain over the surface site. So, then overall rate that for this particular type of single site mechanisms, rate we can write this way. Here K capital S is the overall equilibrium constant or rate constant, you can say K s equals to K small s divided by K minus s, that is forward and backward reactions rate constants ratio. Okay. So, now dual side mechanism also similarly one vacant side is also there. So, that also take part in the reactions. So, when reactant A get adsorbed over the surface side. So, this type of mechanisms we can write this way. So, this is A occupied, this one, and this is vacant site or surface sites, you can say. When both come in contact, means when for conversions of the reactant A, it required two different active sites of the catalyst. So, then it converted like this and this. So, the rate for this type of mechanisms we can write this way, rate of surface reactions if there is dual site reactions. Okay. So, here similarly Ks is there, Cas concentrations, this is vacant site concentrations, here minus C concentration of Bs, concentration of vacant site divided by Ks. Similarly, rate of forward backward reactions if we consider, and this way we can write. Okay. So, now dual side mechanisms usually find it this type of mechanisms or this type of surface reactions is called Langmuir-Hinsel type of kinetics. So, here if we take one example, CO oxidations to formation of CO2, means CO plus oxygens you are getting CO2. So, this is the reaction. So, here two reactants molecules, one product formation is there. So, here CO the reactions was conducted over, let us say platinum, that is the catalyst that was taken, that is the active sites. So, here one side is occupied by CO, another side occupied by the oxygens atoms. So, then react and converted this product. So, this way you can express or write this way also. Okay. So, then the generic rate equations, general rate equations we can write this for component CO and for oxygen Bs, and then so this is actually general equation. So, we have written, so this is for A plus B converted into C plus D, for that systems A plus B converted into C and D. So, there A reactant occupied surface sites, B occupied surface sites B, and once reactions is there, component C or component D formation is there. So, then corresponding rate equations is like this. Okay. So, here see two similar sites occupied, both are platinum. So, if the catalyst surface sites are different, so one is platinum, another is iron, this way also we can write. Okay. So, then surface sites A is platinum, this is, and this is S prime is the iron. So, S prime we are saying irons and S equals to platinum. Here S is platinum. So, here both the surface sites are platinum, same sites, here may be different sites, that depends on the catalyst that we are preparing for a particular reaction. So, either may be bimetallic catalyst or monometallic catalyst. If monometallic catalyst is there and the mechanism is dual side reactions possibility is there, then so we can say reactions surface sites we can express this way, or if it is two different sites are there. So, this way also we can write the rate of reactions. Okay. So, this type of reactions usually are mechanisms usually called Langmuir-Hinsel type of mechanisms. Okay. So, Eley-Rideal type of mechanism, that also we said. So, one reactant molecule C, if A plus B is the reactant, surface sites is there, here it is converted into product C in presence of these sites. So, A must be occupied surface sites and B remain in the gas phase. Okay. So, both will react and it would give product. So, it is here like C, propylene plus benzenes, if we react in presence of any catalyst, it would give cumene. Okay. So, in this case propylenes remain in the gas phase, benzenes occupied some surface sites, and then reactions will take place and cumene production should be there. So, these reactions we can write this way, these reactions propylene in the gas phase B, benzenes A, and cumene is the C. So, this way you can write this, or you can make that balance this way. Okay. So, rate of reactions we can write this. So, considering the adsorptions of A and B in the gas phase, therefore, the surface concentration of A we are expressing C, and B since in the gas phase, therefore, we are expressing or putting that concentration of B in terms of partial pressure of that component, and here cumene is the product that is remains in the adsorption phase, therefore, we are expressing CCS concentrations. Okay. So, now means adjacents we have studied, surface reactions, various type of surface mechanisms we have discussed. Now, the third step is the desorptions. First step is the adjacents, second step is the reactions, third step is the desorptions. So, these ones we have discussed. Now, this we will discuss desorptions from the once reactions is over, product formations is there, that product would be desorbed from the surface sites. Okay. So, in the desorptions case, let us say this is the desorptions reactions CS, that is the product formation C is there, C plus B to C formations is there, C is the product, reactions is over there. So, now reactants that product formed products that would be desorbed from the surface side. So, if it is this is the product remain in the adsorbed way, and once it is desorptions, product C formation is there and surface side remains inside of that catalyst. Then rate of desorptions reactions we can write RDC, that is equals to Kd into CCS minus Cv into Pc by Kdc. Kdc is the desorptions equilibrium constant. Okay. Kdc is the desorptions equilibrium constant, and when this is the Digestion reaction, that is the reverse of adjacent reactions. If Q mean was adjust at this surface sites, it would give the reverse reactions, we can say it is adjacent, and forward reactions that we can say that is desertions. So, adjacent rate would be minus DAC, just reverse signs, negative signs we can put it here. So, rate of adjacence equals to rate of desertions, that we can express just opposite signs. Okay. So, then rate of desertions constant equals to 1 by Kc, Kc is the adjacence equilibrium constant. Okay. So, then now KDC we can substitute here in terms of 1 by Kc. So, the equations, these equations we can write this way. Okay. RDC rate of desertions equals to Kd, small kd equal to rate of forward reactions. Okay. Kd minus d, that is the backward reactions rate constants. Okay. So, this is forward reaction rate constant, backward reaction rate constant. So, the rate of desertions reactions we can write this way. So, now 3 reactions we have considered. 3 reactions means rate of adjacence, rate of surface reactions, rate of desertions. So, 3 different rate equations we can get. Rate equations for on the basis of adjacence we can get one adjacence surface reactions, for that also rate, and desertions for that also D. So, this way 3 rate equations we can get. Okay. So, now question is what would be the rate limiting steps. So, either 3 reactions simultaneously will take place, means adjacent surface reaction and desertion. So, from that which one would be the rate limiting. So, either maybe this one rate limiting, or maybe this one rate limiting, or maybe this one rate limiting. So, which one we do not know. So, we have to conduct the experiment, based on that so experimental data will be extracted, and then these 3 rate equations you have to consider one by one. So, you have to consider which one would be the rate equation. Based on that rate limiting steps we have to discuss. So, that we can give one example, then so we can it would be clear. Okay. 3 reaction steps are there, adjacent surface reactions and desertions. So, at equilibriums what would be minus RAD prime equals to RAD RS RD, adjacent surface reactions and desertions reactions, all the rate at steady state. Okay. So, 3 reaction steps are equals. Okay. So, one particular steps, if we consider this one is rate determining step or rate limiting step, that is the rate controlling step. So, then what would happen? So, rate constants would be very high for this reaction. Rate constants would be so much so high that, so RA minus Ka equals to 0. So, this is rate we can write this way, minus R equals to Ka into some concentration difference. So, that we can write. So, if these steps adjacent step is rate determining steps, so then this part would be very high. So, once this rate constants would be very high, so then minus RA by Ka close to 0 you can say, or it may be 0. Okay. Rate would be negligibly very small. Okay. So, that therefore, that would be the rate limiting steps. So, once it is rate limiting steps, so then that considering that rate limiting step or that reactions is the very crucial for that particular all reactions. So, then we can find out a particular rate equations. So, first we will consider these reactions as a rate limiting step, next we will discuss surface reactions, and then rate of desorption, so that is the rate limiting steps. So, which one we do not know. So, considering each reactions will develop corresponding rate equations. Okay. So, that would be now our task. Okay. So, here adjacent desertions for ammonia productions, nitrogen to hydrogen, that are the reactants. Nitrogen and hydrogen both are reactants, ammonia is the product. Here one example you can see. So, here adjacents of hydrogens, nitrogen adjacents, and then nitrogen dissociations, then surface reactions would be there, NS plus HS, that would gives by consecutively these are the step by step reactions. Ammonia productions is there, means here nitrogen and hydrogen adjacents is there, and then nitrogen's surface reactions, ammonia productions is there. Then third step, desorptions of ammonia. So, this way we can write these reactions 1, reactions 2, reactions 3. So, most of the cases it has been observed that the adjacence of nitrogen is the rate limiting step, rest are the rapid reactions, but this is the very slowest reactions. So, based on that overall the reactions rate would be slow. Okay. So, it may be rate limiting step. So, that we do not know, but we can guess that one by once, and based on that overall rate equations will be developed, and once that rate equations is fitted with the experimental results, we can say that the guess whatever we have guessed, so that was correct. If it does not fit with the experimental results, then we can say that our initial guess was wrong. So, then another guess we have to consider, and then another rate equations we have to develop, and then that if it is fitted with the experimental results, then we can say that that particular steps whatever we have considered for that particular reactions is the rate limiting steps. Okay. So, now we have to develop Langmuir-Hinshelwood type models, rate equations we have to develop. So, for that one examples we will consider. So, here we are considering cumene to benzene and propylene formations. So, here C is the cumene, B is the benzene and P is the propylene, that we are expressing. So, okay. So, adsorption reactions we can write this way, surface reactions we can write this way, and then desorptions reactions we can write this way. So, here propylene was taken in the gas phase and benzene and cumene both are occupied the surface sides. Okay. So, this way means reversible reactions for step 1, step 2 and step 3 means adsorption reactions, surface reactions and then desorption reactions we can express. Okay. So, now if adsorption reactions is there, so then we have to develop rate equations. Okay. So, rate equations we have developed for adsorption reactions, this is the adsorption rate equations. Okay. So, or we can write this way, and vacant sites also we have to substitute here. Okay. So, what are the other various component parameter that is given here, or that is expressed here. What is RAD, that is the rate of adsorption, CCS that is the adsorb means mole of cumene that is being adsorbed per gram of catalyst. This is rate constant forward backwards, this is overall equilibrium rate constants. Okay. So, now surface reaction steps is the surface reaction. Similarly, surface reactions rate we can get, or we can write this way these reactions also. So, this way we can write the corresponding rate, forward reaction, backward reaction rate constant and overall equilibrium rate constant. Okay. So, now similarly for step 3, that is the desorptions, rate of desorptions if we consider the reactions is this, and then the rate equations we can write this way. Okay. So, in the rate of desorption similarly, so we can express desorption rate constant equals to inversely proportional to the absorption rate constants this way, KdV we can write this, and we can substitute this here in terms of Kb we can get. Okay. So, now means considering 3 reactions we can get 3 different rate equations. So, now here Cv side balance also we have to consider Cv. So, that also we have to substitute here, and then it would be different or simplified equations would be there. So, now considering each adsorption cumene is the rate limiting or not. So, then if we consider the adsorptions of cumene, this is the rate limiting step, RDA step, rate limiting step or slow steps. So, here rate constant would be very large, then overall rate would be very slow or 0. So, then we can considering first we have to guess based considering these equations, and then surface reaction is this and desorption reactions is this. Okay. This is reactions 1. So, we are considering that this reaction is the rate limiting step. Okay. So, then what would happen? So, this means here Ks would be very large and Kd also would be very large. So, then Rs by Ks, Rd by Kd would be 0. So, from surface reactions and desorption reactions we can get this. Okay. So, then if we put this rate equals to 0, this rate equals to 0, so then we can get this and this. Okay. So, now you see a surface concentration of the C and surface concentration of B we know. So, now in this case rate equation CCS is required, CCS we can substitute here directly. So, once we substitute this CCS in these equations, so then the final rate equations would be this, means by considering adsorptions, cumene adsorptions is the rate limiting step. So, these equations we can develop. Okay. So, now this equation side balance also we have to do, overall side balance I said. So, now means from the adsorption reactions and desorption reactions, surface reactions and dissolved reactions, once we put rate equals to 0, then B concentrations and surface C concentrations we know. So, these are the equation 2 and 3, from 2 and 3 we can get these two. Okay. So, if we do the overall side balance, Ct equals to, we can write Ct equals to Cv plus Ccs plus Cvs. Cv we can put this, but Cs is we can substitute here, Cv we can substitute here. So, after substitutions Cv we can get this way. Okay. So, now this Cv we can substitute here, so that will come later. So, here these constants we can express this in terms of Kp. So, Kc, Ks and Kb we can writing in terms of Kp. So, then these equations we can write this way. Okay. And now Cv we can take out from the reactions equations, and then Cv we can substitute here. Then we can get these equations after substitutions. Okay. So, now this we can get. So, if we consider the initial propylene concentration, benzene concentration is 0. So, then the rate law can become like this, and it would be like this. Okay. So, if we plot initial rate of cumin concentrations in, with respect to the partial pressure of the cumin, so it would be linearly increased. Okay. So, that was the guess 1, means earlier ones we have considered this one as the rate determining step. Now, surface reaction is the rate limiting step. So, then we have to focus on this, means this is as a our guess 2, that is the this reaction is the rate limiting step. Okay. So, neither this neither not these are not the rate limiting steps. This one is the surface reaction, this is the surface reaction, step 2 is the rate limiting step. So, based on that means surface reactions rate is this, and adjacent reactions this is 1, this is 3, and this is reaction 2. Okay, rate equation. So, these two are these reactions 2, that is the surface reaction, that is the rate limiting step. Okay. So, then keeping aside these reactions, other two reactions is theirs. So, these are the two digestion rate, this is adjacent rate. So, here K is very large and Kd is also very large. Okay. So, once these are the two very large, so then this we can say that Ra by Ka, that would be 0, and Rd by Kd equals to 0, since these are the very large value. So, rate would be negligibly small. So, therefore, it would be 0. So, by putting these two in this equation 1 and 3, we can get Cb concentration, Cc concentration. So, and surface sites balance also we can do from theirs, if we put theirs. So, Cv we can get this. Okay. So, now B concentrations and surface C concentrations we know. Now, surface B and C concentrations we can substitute these equations. So, after substitutions we can get these equations, rate equations, and here capital Kb equals to Kc Ks by Kb. Okay. So, now this is the surface rate equations. So, here Cb vacant sites in terms of other component or partial pressure of benzenes and cumins we can express this way, and that we can substitute here. Once we substitute it here, so then we can get this is the rate equations, or also simplify we can consider small Ks, Kc and Ct. So, this multiplied with each other, that is equal to small k, also we can this way you can write. So, here to make it more simple. Okay. So, then this equation, this is the rate equation. So, once surface reactions we are considering as the rate determining step or rate limiting step. Okay. So, if initially no product formations is there, so partial pressure of propylene and benzene, so that we can say equals to 0, and partial pressure of cumin, that is equals to initial concentrations. So, if we put Pp equals to 0, Pb equals to 0, the places where it is available. So, then the rate equations we can convert this way. Okay. So, if low partial pressures case 1 and case 2, if high partial pressure of cumins that we are placing inside of the reactors. So, then if low partial pressure of cumin, then we can say this in the denominator terms 1 plus Kc Pc 0. So, 1 should Kc P 0 Pc 0 should be less than very less than 1. So, then we can neglect these terms and then the equations can become like this. So, this is the special cases that we are considering. So, rate very linearly vary with partial pressure of Q means. So, rate linearly vary with the partial pressure of Q means and low pressure. Here you can see at low pressure it is linearly increase, and so when pressure is the high, so then in the denominator of these equations, so this part would be very high as compared to the one. So, it is independent of rate independent of partial pressure of the Q means. So, here if we further increase the partial pressure, it does not changes, it becomes plateau. Okay. So, then rate does significantly does not change with increasing high partial pressure. So, the rate equation should be like this in this case. Okay. So, now surface reactions as a rate limiting steps we have considered and we have developed the rate equations. Okay. So, now gauge 3, gauge 1 and gauge 2 was there. This is the gauge 1s, this is RDS we have considered, reactions surface reaction RDS that also we have considered. Now, surface desorptions, that is the RDS we are considering, this is the gauge 3. So, which gauge is correct that we do not know, but one by one we have to guess and based on that we have to develop the rate law or rate equations. So, in the third case desorptions when is desorptions is the rate limiting. So, then we can write desorptions equation this. So, this is equation 1, this is equation 2, this is equation 3 for the rate of desorptions. So, these equations we are considering RDS steps. Okay. So, then these two rate constant Ka and Ka should be very large. So, then we can write Rs by Ks equals to 0, Ra by K equals to 0, and from these two equations we can get concentration of the B and concentration of the C, that is get adsorbed over the surface of the catalyst. So, CBS and CCS we can get, and that we can substitute in this CBS we can substitute here. So, then we can get in terms of partial pressure of cumin and propylenes. Okay. So, if we after substitutions we can get this. Okay. So, CBS here substitutes we can, and then we can simplify these equations and total side balance based on that also we can do. These are the two we can find out, and then total surface sides balance we can do this way, and here CCS, CBS we can substitute, then CV equals to this way we can write, and that we have to substitute here in these equations. Okay. So, now at the ends we can get this equation, this is the final rate equations. If we consider desorption step is the rate determining steps or rate limiting steps. Okay. So, in this case if we consider also that initially there was no product formations, so then partial pressure of propylene and benzene that would be the 0. So, if we put these are the two components as 0, propylene and benzene, initial concentration of propylene and benzene is 0. So, then this equation should become this. Okay. So, rate would be independent of the initial partial pressure. So, then if we increase the partial pressure of Q means and the rate would follow like this, a straight line will come. So, independent of initial concentrations or initial partial pressure of the Q means. Okay. So, it would be like this. So, now three different rate equations we have developed means by considering means adsorptions as the rate determining steps, surface reaction is the rate determining steps, and rate desorptions is the rate determining or rate limiting step. By guessing three guesses, three different rate equations means this is equation 3 you can see, and equation 2 for surface reactions, this is equation 2 that we have developed, and equation 1 so that also we have developed. So, this is adsorptions reactions, this is equation 1. Okay. So, these three rate equations we have developed. So, which one should be fitted with the experimental result that we do not know, but we have developed by considering Langmuir-Hinshelwood type of mechanisms, we have developed three different rate equation by guess 1 adsorptions as the rate determining step, guess 2 is the surface reaction is the rate determining step, and considering that we have developed one rate equation, and third one is the desorptions of that product from the surface, considering as the rate determining step or rate limiting step, we have developed third rate equation. So, 3 different rate equation we have developed by considering Langmuir-Hinshelwood mechanism, by considering one particular reaction. Now, we have to solve that, means with the experimental data we have to fit those equations, and which one would be the rate determining step, actually that we do not know. Once either 3 equations, if one of those equations is fitted with the experimental results, then we can say that that particular steps is the rate determining steps, that may be steps 1, maybe desorptions, maybe surface reactions, or maybe adsorptions. Okay, so that way we can guess, that we will discuss in our next class. Thank you. So, today is up to this. Thank you.